Truss analysis. This video will cover the part of the engineering civil structures syllabus which encompasses the mathematical calculations regarding trusses, primarily in bridges or other civil structures such as telephone posts. Now, the whole point of this in the civil structure syllabus is to determine calculations for the stresses within members, the reactions at supports, and demonstrate understanding of how different stress situations apply to a bridge that impact safety and usability applications. So what's important to note for this is there is a standardized process for approaching the mathematical questions. If you apply that process, you'll be able to get the questions right, and that's what we'll go through in this video. So first of all, what is a truss? A truss is quite simply a support structure made up of individual members, and these members have forces acting on them, and the forces act at pin joints, which spreads out the force throughout the different members, increasing the strength of the system. So each truss will also have supports. There are two different supports you can have. You can have your roller support, where there are wheels at the bottom of the support, usually indicated by little circles like that. And this basically means it can move from side to side. So any reaction force it creates will always be perpendicular to the horizontal surface it is on. In contrast, a fixed support can have perpendicular or horizontal reaction forces. So you can have a reaction force in the X and a reaction force in the Y, and then combining those, you end up with a resultant reaction force. Also in trusses, you can have two different types of loads. You can have a concentrated load, which is the most common one, which is where you'll see a load acting on one point in the beam, whereas a uniformly distributed load is a load that is applied by something such as wind that is across an entire surface of the structure, and it's usually indicated by arrows like this. And all it means is if you say had a UDL of 10 newtons per meter, every meter you have a force of 10 newtons acting downwards. Reaction forces. So in a truss that is loaded, such as this one here, we have 30 kilonewtons acting at this point and 25 kilonewtons acting at this point. Since the truss is not moving and must be in equilibrium, we must have reaction forces acting at A and B. We will name these reaction A and reaction B. Now note here that reaction B is a roller support and reaction A has a fixed support. So how do we go about calculating these supports? Well, there are three different calculations we can use in a truss that is in equilibrium. So in equilibrium, we have to have three things. The sum of forces in the X direction must equal to 0. So that's forces acting this way and this way must equal 0. Sum of forces in the Y direction must equal to 0, so this way and this way. And sum of moments about a point must also equal to 0. So let's go about trying to work out the reaction forces. So if we take our first equation, sum of forces in the X direction, we get an expression such as this. So sum of forces in the X must equal 0. Let's pick a direction to be positive. We'll go this way is positive. So we have our unknowns. Only reaction force A can have a force acting in the X direction because reaction B is a roller joint, so it's only going to go upwards. So reaction A, X, and then there's no other horizontal forces, so that must equal 0. Excellent, so we found one part of our reaction force. Let's go to the next equation. Sum of forces in the Y must equal to 0, and we'll pick upwards as the positive direction. So what do we have? We have negative 30 from here. We have negative 25 from there. And then we've got our reaction B. So plus reaction B because it's acting upwards. And then plus reaction AY must equal to 0. but this doesn't really help us at this point because we've got two unknowns. So we have to go to our third equation. So we'll take moments about a point. Now, when you're taking moments, it's always easiest to get rid of as many unknowns as you can. So when you're taking moments, it is the force times the perpendicular distance to the point. So if there's any forces acting through the point, the perpendicular distance will be 0, and therefore you don't need to worry about those forces in your calculations. So we're going to take sum of forces about the point A, because we have two unknowns here. Well, we know that this one doesn't exist because we just calculated that, but we've got an unknown here. So by taking a moment about there, then we'll only end up with one unknown, and it'll give us the reaction force for B. So let's do that. So sum of moments, about the point A equals to 0, and let's pick a direction to be positive. So if we take this 30 kilonewtons here, it's acting down like this. Where's it going to turn the bridge about that point? It's going to try and rotate it this way. So let's say that going clockwise is positive. So 30 kilonewtons has a perpendicular distance of 1, and 25 kilonewtons also turns the bridge that way. So it's positive and has a perpendicular distance of 2. And the other force, so reaction B, is going to turn the bridge that way about the point A, and it has a perpendicular distance of 4. So we're going to go minus 4RB must equal to 0. And if we solve that, then we get 4RB is equal to 80 kilonewtons. So RB is equal to 20 kilonewtons in the upwards direction. Excellent. So now we've got our reaction force in B. What we can do with that is we can now substitute this into this equation here, and we get sum of forces in the y, minus 30, minus 25, plus 20, plus RAY, almost equal to 0. So if we chuck that in the calculator, we have minus 40 plus reaction AY equals to 0. Reaction AY equals to 40 kilonewtons upwards. Perfect. Now, if we had a force in the x direction, what we would have to do is we would now take the reaction in the force in the y direction and the reaction force in the x direction, make a little vector diagram here, and this would be our resultant vector, and we can find that by taking Pythagoras' theorem, and let's call this x, y, and it would be x squared plus y squared, square root of all of that, and the direction, so we can call the direction theta, it would be at an angle of tan inverse of y on x to the horizontal upwards like that. Excellent. In the next video, we'll go through finding the forces in individual members.